Are you okay with the kind of controls up there? That's fine. That won't get in the way.
Or shall we fold this?
Yeah, just upload it. Video. Yeah, I think that's fine. Yeah,
That's good.
No theory. No theory.
Yeah, that's right.
I'm going to put your picture next.
No, that's okay.
Okay. Shall we start? Next up, we have Professor Phaun Ong from Princeton. Phaun got his PhD from UC Berkeley and then was an assistant professor at USC before he moved to here. And he has very broad research interests in fields like high-TC, like quantum topological materials and quantum state liquids. And today he will lecture about thermal transport measurement in the titanium chloride. Let's welcome the speaker.
Okay, thank you. Can everyone hear me? Okay, so I took the opportunity to slip in a lot of intro slides to beef up my talk, because the one that I give usually at conferences to experts in the audience. So hopefully this will be helpful. Anyway, first, so what I want to talk about is provide a gentle intro to this problem of the thermal Hall effect, which has become quite topical in the last 5-6 years because of this claim of half quantization in the Kitaev magnet. So there are a lot of moving parts and a lot of new concepts coming together, and it's a good example, I think, of how experiments can engage with theorists on a really nice, juicy problem. So the main player from my side, or the Princeton side, is Peter Checker, and he obtained a lot of help from other grad students and former grad students, Tongao, Max, Hirschberger, and Nick Quirk. And the Oak Ridge University of Tennessee collaboration led by David Mandras and Steve Negler, and provided a lot of nice samples. So the talk is comprised of 2 parts. I will spend most of my time on the thermal Hall conductivity because that's the main topic here. And the slides I slipped in introductions to the Berry curvature, not so much Majoranas, chiral edge modes, and eventually a transport measurement of the Chern number, which I found to be quite interesting. Then if time permits, I will talk about what I think is a more important finding, the observation by these guys of oscillations in the thermal conductivity in the putative quantum spin liquid state. Okay, and if I don't get to cover this topic, both have appeared in one of the Nature periodicals, both subjects. Okay, as all of you know, spin liquid was proposed by Anderson a long time ago in '73 in a somewhat obscure publication, actually, but it's now become extremely well known. If you have what's called geometric frustration in a lattice, so the lattice is perfect. There's no disorder in the lattice, right? So it's a perfect material, perfect spin Hamiltonian. But if you have this notion of geometric frustration, it can preclude the onset of long-range order, no matter how low you cool. And so experimentalists measure this inability to order by the ratio of the mean field exchange that you obtain by measuring inverse chi versus temperature, right? When you extrapolate inverse chi versus temperature, the intercept with with the x-axis will give you a characteristic temperature, right? So even though mean field is not a good guide, it gives you some idea of the ordering temperature. But in reality, if the system still doesn't order, when you get down to 1 millikelvin, the ratio of 1 millikelvin to the inferred mean field temperature gives you a measure of the frustration. So, sorry, I should have included a slide on that. But anyway, because of this geometric frustration, it never orders. And the state that you get at 0 Kelvin is one of the most challenging states confronting us today. And there are no solutions, although there's an enormous amount of theoretical progress. And Xiao Gan has been a leading proponent of this, all these very high-powered theoretical approaches. Now, what's geometric frustration? So in an illustration.
By the way, what is you looking for?
Oh,
Spin liquid?
spin on, yeah. This is the last known photograph of his before he passed away. He did it on the occasion of his birthday. So I think it says here, "Happy birthday, Phil," or something like that. But he was, the silly note, right? What else is hidden? You can sort of see he's sort of disappointed. Anyway, I thought it was a lovely photograph. He passed away about a few months after this picture was taken. Okay, geometric frustration, I'm sure you've heard of it. If you have a triangular lattice, right, and it's antiferromagnetic, all the red moments on one sublattice, on the red sublattice, say point down, and the white sublattice moments point up. The one in the middle now is conflicted, doesn't know whether to point up or down. So that, in a nutshell, is geometric frustration. The lattice has no disorder, but it's just this kind of frustration that caused Phil to propose the state. And a big role played by Phil's own work is this RVB. So you form singlets, and that already involves entanglement. You form spin singlets between all possible pairs, and you call that the resonating valence bond state. So one picture of the possible ground state is you expand it in terms of all possible local pairs. Right? And a nice review of this field is given by Leon Ballance and Savary. Okay, we're not going to solve this problem, obviously, but it sort of sets the stage for what I want to talk about. Kitaev in 2006, maybe a little earlier, proposed another path to spin liquids, and this is sort of interesting. This one involves not so much the lattice, the geometric frustration, but what I think should be called exchange frustration. Okay, the Hamiltonian looks like this, and it looks like an Ising model. Sigma is an Ising, spin half up or down operator, but they are coupled depending on a specific direction in space. So along X, they couple together nearest neighbors with an exchange Jx, and along Y similarly. So one way to picture this, this is all set in a honeycomb lattice, which is this, is to color all the bonds, red, green, blue, for example, and the spins that are parallel or in this case, anti-parallel to the red bond coupled together through a specific red exchange, and the blue ones as well, and the green ones. And then the coupled pairs do not couple to other pairs. So this is a bit artificial, but Kitaev could solve it. And he could solve it exactly by using Majorana representation. Now, of course, this is well beyond my pay scale. So I'll just tell you about his solution and what the implications are. So you represent each spin by 4 Majoranas, right? 3 of the C type, so they lie along the 3 bonds pointing to the moment, and B lifts at the node itself. And using this and exploiting the commutating relations of the Majorana, you could come up with an exact solution. So for us, the interest is in the exact solution, right, to the ground state at zero field. Once the field is finite, nothing works. It is still a well-open question. The excitations are Majoranas and vortices, sometimes called visons. So there it's set, right, an exact solution.
Yeah, just to make a comment that, in the REB approach to high density superconductor, people develop this slave particle approach.
Right.
If you apply that approach to this Kitaev model, that approach became exact. Actually, you'll get the same results.
Oh, is that right?
Yeah.
Yeah.
So, because by that time, the people applied this for the Heisenberg coupling, not for this kind of coupling. And if you apply for this coupling, the slave particle approach became
Great. Thanks for that comment. Yeah, I welcome any comment that you guys might provide. So not just from the older theorists, but anyway.
What do you mean older?
Okay. So this looks very well. All the experimenters obviously were very excited that this appeared, and the search ignited, and lots of folks started working on this problem. Jackley and Kalulin at Max Planck Institute sort of showed the way how, using solid state chemistry, you could perhaps realize this Hamiltonian. So I'll briefly describe their work in the next slide. And they didn't identify the particular material, but thanks to work from the Oak Ridge group and Steve Nagler and a few others who were working on this material, this immediately became the closest approximate. And just like bee to honey, everyone gravitated towards this material. And so that's what I will be talking about. So as all of you know, when you have this octahedral environment, here is a ruthenium surrounded by chlorine in a cage, right? The octahedral cage. So this just looks like the cuprate problem. Like you remember it, the cuprate problem, that's copper surrounded by oxygen. The degenerate 5D manifold splits into what's called the EG, consisting of a doublet, and the triplet, the TG, T2G states. And this is a very big gap of the order of EV to 5 EV. But in the presence of spin-orbit coupling, these three states are further split, and now J is a good quantum number into the 3/2 and the 1/2 states. And if you have only one hole in the ruthenium, it will occupy the state, which gives you an equivalent spin half. It's not really a spin in the sense that we think of spin, but it's a doublet. Now here's the nice thing about Jackley and Kalulin's work. They pointed out that now we're looking down at the plane. Let me see if I can, focus on this pair here, right? You can see that the horizontal plane includes the two ruthenium atoms, and the nearest neighbors are two chlorine that are equidistant from both moments, right? So I copy it here. This is the plane including the two ruthenium moments, and they talk to each other directly. That's called the direct exchange, as well as the through the chlorine, that's super exchange, right? Now this is what's nice. So here's quantum interference at play, although we cannot manipulate it. There are two paths that are equivalent, right? One going from here to here, and the other one going to the other, through the other chlorine. And it turns out that they interfere destructively. And that's enough to kill the direct exchange. Not completely, but to suppress it relative to what we're looking for, which is the one that gives rise to the Ising exchange. So at the end of the day, these two coupled together, the moments, right? The moments that are parallel to the perpendicular vector here, which is what we call the Kitaev axis. And that's the largest coupling term, or we hope. So if that's the only term, then we have realized the Kitaev. Right? So it's this very fortuitous interference between equivalent paths. This is similar physics to Kagome flat bands, right? These interferences play a central role.
Sorry, can I ask? So it's basically like quasi-2D material.
It is, yeah. So
and the interaction between layers is
this will become apparent here. Yeah. Oh, sorry. Let me go to. Yeah. Okay, so here's the Hamiltonian again. The material is comprised of honeycomb layers, and it's drawn in perspective. I hope you can see that this forms a hexagon, the gray atoms. Right? If you look down from the top, it will define this hexagonal unit cell. Each one, at each vertex is a ruthenium local moment. The green dots are all chlorine, and they are going to be irrelevant. They have done their job. So we only want to focus on the gray, the large gray moment. Okay, now there are 3 such planes that I mentioned, right? So remember I showed this figure. The plane, including the 2 ruthenium atoms, is now drawn horizontal. And I purposely colored it pink to associate it with the perpendicular Kitaev vector. So these are called the Kitaev spin vectors. They are completely unrelated to the lattice vectors. But since this will be used a lot in the literature, if you read any of these papers, it's good to know what they refer to. So the lattice vectors I call A, B, C, which will play an important role subsequently. But the Kitaev spin vectors are perpendicular to these planes. Now the pink one is sort of tilted. Hopefully this is apparent. Because the octahedra lie on one of their faces. They are not standing vertical, right? They lie on one of the faces. So the pink plane is tilted, and therefore the Kitaev spin axis is likewise tilted because it's normal to that plane. Similarly, you can define 2 other planes. The blue one, which is this, right? It's tilted, and now the Kitaev spin axis coming out towards you, and the green one is tilted this way. So from the comparison, you can attempt to associate these exchange terms with the Kitaev term. And as I said, the original material identified was iridium something, but pyrochlor, but that didn't really show any promise. This was the material that showed the promise. And so for the last 15 years or so, a lot of work has gone into it, mostly neutron scattering and the usual thermodynamics, heat capacity, and so on, magnetization. Okay, here's the phase diagram of ruthenium chloride with the spin. Okay, the spins are all living in the honeycomb layer. So now this is looking top down, right, on one of these honeycomb layers. There are terms, unfortunately, in the Hamiltonian. These are called gamma terms that do not belong to the Kitaev Hamiltonian, right? Because nature is never so cooperative to provide a material that can be described by a Hamiltonian that you invent. So there are other terms, gamma. I think these are the direct exchange terms. They induce long-range order, so that spoils the spin liquid eventual spin liquid at low temperatures, right? But the transition temperature is very low. So if you look at this phase diagram, if you come down in 0 field, it orders at about 7.5 Kelvin into this state, which is antiferromagnetic, and it's comprised of local moments that zigzag along the A-axis. So you may remember from graphene, this is called the zigzag axis, and the perpendicular axis is called the armchair axis. Armchair, I guess, is because this looks like an armchair. But anyway, so hopefully this is familiar from graphene. Now these 2 axes play a big role. They have very different characteristics. The exchange is very feeble, right? Because most of it, as I mentioned, was canceled by quantum interference. And that's why the transition, the Néel temperature is very low. So one Kelvin exchange is equivalent to 1 Tesla, roughly. So a 7 Tesla field is enough to kill the order. And indeed, that's true. If you apply the field along the A-axis, by the time you get to a little bit over 7.3 Tesla, you suddenly remove all the zigzag order. So not all hope was lost, right? So even though the Kitaev scenario wasn't realized down here, you could kill it. You could kill the order, and perhaps this was the quantum spin limit. And lots of experiments, especially neutron scattering, showed tantalizing evidence that this indeed was a highly disordered state, which eventually was destroyed at high fields, because now all the moments line up with the field by the Zeeman energy, and you destroy all spin-liquid correlation. But anyway, there's a nice window here that may have interesting properties. So this is the situation in 2016, 2017. Then the group in Kyoto, my former postdocs, Professor Hara and Matsuda, published, out of the blue, this paper that captivated the whole community. So this is their finding.
Excuse me. So in addition to magnetic field, whether there's some other toning parameter you can tone to change the.
In addition to magnetic
In
field.
addition to this magnetic field, whether there's other.
People have tried strain, but it doesn't do very much.
What happens if you tune in different direction?
Oh yeah, lots of people have rotated the field on there. It turns out that the component of the field along the A-axis, along the zigzag axis, is the one that the system pays attention to. So everything changes like the cosine of theta.
I remember you mentioned that the original graph theory only works at e equals 0. So how does this still support the constant?
Yeah. So this is So the original calculation by Kitaev referred to zero field. But you can then what he did, and this is relevant to the thermal Hall conductivity. He used the applied field as a perturbation. So you can sort of perturb around the exact ground state. Now, whether the perturbation still holds at a field of 7 Tesla. But anyway, using the field as a perturbative factor, as a perturbation, he found that to the third order in the field, in the weak field, you get a thermal Hall conductivity that is half quantized. So he predicted that. And so this is known to everyone. And that's why I said the Kyoto group dropped a bombshell, basically, saying that they had discovered the final solution. Other questions? I have lots of time, so I can address these questions. So this is Matsuda's data. The geometry of the experiment is, you apply a temperature gradient along this direction. And then they found that there is a finite thermal Hall effect. So this right edge is slightly warmer than the left edge. So that represents a Hall effect of heat current, not of electron. There are no free electrons in this material. The gap is very large. But amazingly, the magnitude of the thermal Hall effect, when divided by temperature, so you're always plotting kappa xy divided by t, seems to show a plateau. But only in a very restricted range in field. Here it's from 7 to 9. And temperature is between roughly 3.5 to 5. So a very narrow temperature range. So obviously, everyone asked Matsuda, why don't you go colder, right? Because any quantization gets increasingly sharper as you go colder. And I forget what he said, but anyway, so this inspired us to repeat the experiment because it's so intriguing that you have a crystal that's beautifully grown and all that. It's just a layered crystal. and it's swimming with Majorana's, right? You don't need to proximatize the needle, you don't need to have all these device type manipulations. This is just a chunk of material with the magnetic field in the right direction. This will be swarming with Majorana's. Actually, in Kitaev's theory, the bulk of the crystal develops a gap in the spin excitations. The spin excitations actually mimic Dirac cones, and the cones develop a gap in the bulk, leaving edge modes, just like the topological insulators. And the edge modes harbor Majorana's, and they zip around to give you the half quantization. I'll describe that more in a minute as we go along. So here's the setup, at least in my group. Here's the crystal, and you attach gold wires, right, to make contact with the edges. This particular wire sinks into the bath, and there are all kinds of stuff hanging onto it. This is the heater. The heater will inject a heat current flowing vertically down. And there are 4 thermometers. I think in this case, only 3 are connected. So there's 1, 2, and 3, right? So you're trying to measure as many points on the edge, the temperature of, to detect the thermal current. Now you can think of the thermal conductivity basically in analogy with electrical conductivity, right? So the heat current JQ replaces electrical current charge density, charge current density. And instead of voltage, you have a temperature gradient, right? So once you make the dictionary translation, you can use all your intuition from electrical transport to this experiment. So we can isolate the resistivity tensor, which I call lambda. So lambda is rho. So rho XX or rho YX. And then if you invert the resistivity tensor, you get the conductivity tensor, which is called kappa. So we measure lambda YX and then do the matrix inversion to derive the thermal conductivity.
You have to take into account the geometrical shape in your sample.
It doesn't matter. Yeah, for transport, the shape of the material doesn't matter because of the Laplace equation. It's very forgiving.
So I think the temperature drop mostly happen at the interface because of the interface thermal gradient, thermal conductance. So how do you evaluate the real temperature drop inside the central region?
Sorry, what's the statement again?
The temperature drop happens mostly
temperature what?
Temperature drop.
Drop.
Yeah, mostly happens at the interface, right?
No. You think of the quantum Hall effect. No, it doesn't. It's uniformly distributed. It's not like the quantum Hall problem where the chemical potential immediately drops.
May I ask a technical question?
Sure, yeah.
How do you keep nice thermal conductance or thermal contact without injecting the current into the sample? Or
yeah, so no, the sample is an insulator, especially at 1 Kelvin and lower. It's an extremely good insulator. So there's no current going to the sample.
Okay.
But the heat is being generated by this heater here. And the gold wire conducts it to the crystal, and then it flows through the crystal to the bath. We're dealing with thermal current density, not charge current density.
Right. Since the sample is an insulator. Okay.
It's an insulator. Well, it could be done with metals as well.
For the metal, then your current that heats up your
well, you don't. It is all within linear response, so you try to avoid self-heating. But anyway, it's all thermal current.
So the picture here is that the thermal conduction goes through the bulk or through the edges?
The what? The theory?
The thermal current goes through the bulk?
We think it does, yeah.
Not through the edges. It's not current.
So that's an interesting point. When the Hall effect comes in,
right.
It's an edge effect. Yeah. Hold that thought. I'll come to that.
Okay.
But nominally, the crystal is uniform, and as a start, think of the heat going uniformly through the bottom. Other questions?
That's a main question. So, so you basically create the gradient of temperature, and then how do you measure heat current? Do you measure it by also by temperature? By the power.
Well, you can by estimating the power generated, and you know the conductivity of all these materials. But it's sufficient to actually get it from the power produced by light.
So I think this setup is applied by your magnetic field. So this magnetic field will generate an eddy current, right? So this eddy current will also contribute to the.
Yeah, good point. Yeah. So because this is an insulator, there are no eddy currents, but eddy currents will be produced in the sink. In this case, we use brass as a sink. So the magnetic fields are fairly large, so depending on how fast you ram them, they could produce eddy currents. But it doesn't affect the experiment, but it comes in when you want to be exquisitely careful of extraneous. So all these questions are good. They are indicative of it looks like a trivial experiment, right? Especially when you translate it. You cannot implement this on what's called the physical properties measurement system that are you mostly theorists? All experimenters know this acronym. Every lab now working on quantum materials will buy a $60,000 or $80,000 system where you put the sample in and the computer does everything. You come back tomorrow morning and you print out the result. This is the only measurement that cannot be done that. It needs a graduate student. The reasons follow.
And it doesn't come with $60,000.
The reason is because thermal heat current goes everywhere. We don't appreciate it when you measure charge current. Nature has given us insulators and metals, so you can basically control the path of electrical current. Not so heat current. Heat current goes everywhere, and sometimes you think it's going this way, but it's going that way first and then coming back. It's a mess. And so, in fact, in the beginning, many salesmen would come and interview us to try to see, well, what's the trick? Can we duplicate it in the next generation of PPMS?
We have a question from the Zoom that is, what is the advantage of using gold wire over silver?
Yeah, it's the contact of resistance. Silver tends to oxidize, so gold is first. But you can use any equivalent metal. There's no intrinsic advantage. Anyway, okay, let's move on. So we realized why Matsuda didn't go below 4, but didn't report, he probably didn't report any measurements below 4 Kelvin. A host of difficult features, phenomena come in to really mess up your measurements. One of this is called the magnetocaloric effect. And the reasons are following. Because the exchange is so small, so this is something that we hadn't appreciated until we did these experiments. The spins behave like free spins. And if you think of the Dulong-Petit calculation that you did as an undergraduate, right, calculate the heat capacity of non-interacting spins, you get the Dulong-Petit value, right, 1/2 kT. And this is an enormous amount of entropy that the spin has. Almost all materials, when you cool down to 4 Kelvin, will lower their heat capacity, the entropy, dramatically. But not if the spins are almost non-interacting. They retain a huge amount of spin entropy. So every time you move the field by even a fraction of a Tesla, the spins are either spitting out a huge amount of entropy or they are pulling it in. And it's so large a entropy current that the phonons basically choke. They simply cannot maintain the crystal in equilibrium. And so you see these non-local temperature rises. So these spikes are when you step the magnetic field incremented, and this is the local temperature, and one of the 3 thermometers basically choking, right? The temperature has gone up, and it is such a huge entropy that even the bath is supposed to be at a fixed temperature. You see, it's being pulled, right? And then the other countervailing effect is the eddy current that you mentioned, right? The bath is also responding to the step increase, but it goes the other way. So that these took a long time to figure out. And so what we do is we step it at these intervals. So here's a step function, and we wait for the system to settle down before taking measurements at this point. So it's sort of like a pump pulse type of measure. Okay, well, one of the interesting, okay, now let's get to the physics. One of the interesting phenomena here is what the symmetry of the problem. All right, so I want to spend just a minute talking about that, because this is a rather cute effect. The crystal has a mirror plane, right? I think this is the honeycomb lattice, right? A, B axis, and the C axis is coming out towards you. The mirror plane is the AC plane. And if you apply a magnetic field perpendicular to the mirror plane as drawn here, you do not break the mirror symmetry, right? So what does that mean? Okay, so you recall that the B field is axial, right? It's an axial vector, whereas everything else is polar. So the magnetic field being axial doesn't change direction when you go into the mirror world. Right? So if you have an observer living in the mirror world, he or she sees the same field direction. However, the polar vectors will change direction, right, if they are perpendicular to the mirror plane. If they are parallel, they do not change direction. So these two behave like your everyday experience, right? If you take a pointer and you stand in front of a mirror, the reflected image will point backwards. But not if your pointer is pointed parallel to the mirror plane. Magnetic fields are really weird, right? They do the opposite. And the best way to understand that is to think of the magnetic field as generated by the curl operation. Anyway, okay, so given this, if you do an experiment here, your counterpart inside the mirror will get the opposite Hall current, right? See, both of you are pointing the field in the same direction, applying the same driving gradient, but the mirror symmetry demands that you see opposite Hall current. So it must vanish. So right away, you predict that if you apply your field along the armchair direction, there should be no Hall effect. Never mind what the mechanism is. Symmetry will forbid it. However, it doesn't forbid it if you point the field parallel to the mirror. This argument fails, and you do indeed, it could allow a finite Hall response. So we checked that, and indeed that's true, right? So we now, our experiments are in what's called the planar geometry, which means that the field is in the honeycomb layer. So the usual Lorentz force is absent, right? There are no electrons. So this is a very strange geometry. It's in the honeycomb layer, and we are looking for a Hall response within the same layer. Let me point out here. So this is the honeycomb layer, and we heat up this edge, right? So we're driving the heat current downstream. Normal Hall effects, like in the quantum Hall effect, the field will be perpendicular to the layer. So we're looking for a deflection of the charge current, right, by the Lorentz force. Here it's completely different. The Lorentz force doesn't come in at all. We are applying the magnetic field in the plane parallel to the applied current. Still, we're looking, there could be a net heat current flowing in the transverse direction. but not if the field is perpendicular to the mirror plane, right, along the armature. And indeed, there's nothing. So this plots the temperature difference between the two edges. Yeah, so the measurement is, we hold the current density fixed and look for a tiny difference in temperature, which I call delta Y. And you see that within our measurement fluctuation, it's not there, even up to fairly high temperatures and high fields. Right? The surprising finding is that if the field now is tilted parallel to the a-axis, right? So in the first panel, the field is pointing towards you. Right? This is a mirror plane. Right? So here, mirror symmetry forbids it. But if you now point your magnetic field parallel to the plane, you see the emergence of a signal, right? What this peak signifies is that this edge is now slightly warmer than this edge, right? But if the field is reversed, the opposite happens. That's a Hall effect. Right? But in a very strange geometry, with the field parallel to the a-axis.
So what was the geometry in 2015 paper? What was the geometry in 2015 paper?
In the 2000
2015
Kyoto paper?
Yeah.
They did, yes, they kept changing their okay, in the very first paper, they had it tilted this way, making an angle. And then they sort of hinted that, well, it's only this component that's relevant. So up then in 2021, I think, they tilted the field in the a-axis. And then they said, well, this is now the correct direction. And then, yeah, and then they see quantization. So that second paper is Yokoi et al. This appeared in Science. And so this prediction, this finding we confirmed. And actually they also mentioned that there was no second one.
So there's no quantization here, right? There's
Yeah.
no quantization.
Yeah. No, there's no signal.
There's no signal.
But this paper claimed that once you tilt it parallel to the zigzag axis, this peak here corresponds to quantization. So Peter Checker polished up the data, and you can see that now you can measure it with a signal to noise ratio that's very good, almost like an electrical measure. So we agree with the Kyoto group that there is this intriguing planar thermal Hall effect. The disagreement is whether this is quantized and what is its temperature dependence. That's the one thing that they didn't report. And you see that that is the key feature that allows us to arrive at our current picture. Okay, I hope the experimental geometry is clear. It's drawn here as well, right? This is the heater. It drives a vertical temperature, a thermal current density. This is the sink. And then we're looking for very tiny differences between these two thermometers.
So the x direction here or the a direction on the upper left, right?
We can choose it, right? In this case here, the x direction is parallel to B. But here it's parallel to A.
I mean, in the setup on the bottom right, for your measurement, you have to pick the x direction parallel to A so as to get a non-vanishing.
No, the other way, So the x is always the temperature gradient.
Right.
The magnetic field can be rotated.
Oh, so the magnetic field does not have to be as the same direction as your heat flow.
That's right. It's a question of whether the magnetic field breaks the mirror symmetry or not. That's the fundamental question. Other questions?
How about the, it looks like these have changed a little bit at the point of kind of peak and local and minimum for what field these occur at. Is that temperature change or are they actually the same?
I didn't understand the question.
So in Peter's data, it looks like maybe the maximum and minimum kind of points are more towards like 9 Tesla, whereas in figure C in the top right, it looks more like 8.
Oh, you mean the field at which this occurs?
Yes.
That's very temperature dependent. So this 4 Kelvin, this is close to 6 Kelvin.
Thank you.
Yeah, it's very temperature. Other questions?
Is there also magnetic field perpendicular to the plane?
We have applied that, yeah.
Is that magnetic field also breaking the mirror symmetry?
Oh, so
Or already breaking the mirror symmetry?
no, it also breaks the mirror symmetry. So remember, okay, here's the,
So then why do we
this is the A-axis, this is the B, right? The mirror plane is this one.
so the perpendicular magnetic
So
field
a magnetic field that is along the C is parallel to the mirror, right?
so it's already
So
breaking.
it would break the mirror symmetry.
So why do you still need the magnetic field along the direction?
It turns out that the phenomenon that we are looking for, this will be apparent. Okay, the reason why we don't apply the magnetic field along the C-axis is because you have to kill the ordered state. Let me go back to the phase diagram. Yeah, this is a good question. See that the ordered state is killed at 7 Tesla, right? If you apply your magnetic field at a tilted, at an angle, it's the component along the A-axis that does the job. So if you apply your field along the C-axis, you will need to go to 150 Tesla. So it will break the mirror symmetry, but it's sort of not doing anything interesting that we care about. So this is the subset of the data, and you can see that the signal to noise ratio is pretty good. The thermometry is behaving itself, and the punchline here is that you don't see any evidence of quantization. And we're going from 3 Kelvin all the way to 9.2 Kelvin, and there's no inkling that there's any plateau anywhere, right? But of course, this is the thermal Hall resistivity, whereas the thing to compare it with, the quantity to compare with theory, is the thermal conductivity, the thermal Hall conductivity. And when you invert the matrix to here, you don't see any plateau. If it's there, it would have appeared here. But you see that even at this stage, if you lower the temperature from, let's say, 8 or 9 Kelvin, it comes down very rapidly. There's no quantization that holds it up there.
So what was wrong with the original data, with the Matsuda?
Well, we kept asking him for the resistivity data. Right? This is lambda. Because there's no point showing this data because, as I'll mention in a minute, you have put this through the inversion machinery. So you hide all your error bars. Here is where it should matter, but you just wouldn't tell us. But no, I don't want to bash him too hard because
just a little bit.
I mean, look, it's exciting when you see half quantization. Right?
Yes.
And so it's very natural to sort of gravitate towards what the theorists tell you without showing the rest of the data.
So you don't have an even lower temperature. The lower temperature signal is too weak to see.
Yeah. So by the time you come down, actually we do. The lowest temperature is this sharp peak. Yeah, actually, I don't know if you can see it. So as you go colder, it becomes smaller in amplitude and becomes a little peak here. You'll see this in the color map in a second. But the point I wanted to bring home here is the following. When you put it through the matrix inversion machinery, you are trying to calculate a quantity that is exquisitely small. So this is your measurement, lambda yx, and it's being amplified by kappa xx squared, which is a huge number. So any measurement here, which you can barely see, has to be multiplied by this huge number. And you can see that if you are honest, you put in all your error bars, you cannot see anything basically. And if you look at their second paper, the one that appeared in Science, they claim that the quantization interval has shifted from here to here. And you say, how could that be? Because it's in our best measurements, this is all noise. It's like you're trying to measure a quantity that is this in amplitude, right? But the error bars are 3 times larger. You invert it and you claim quantization, right? But if the error bars are real, you will just see a hash. So that I think is the more serious problem. But we could have proved the point if they had given us the resistivity data. Okay, so I've talked about this already. So we can convert all this into a color map. And there are 50 curves all taken at fixed fixed temperature, 50 horizontal cuts that we assemble into a color map. And as Xiaogong asked, as you cool down to 1 Kelvin or lower, it is restricted to a very tiny delta function. The signal actually goes negative. The blue part is when the Hall response goes negative. And this was actually predicted by Youngbeck Kim's group. But anyway, we confirm the finding in this paper insofar as there is a in-plane thermal Hall effect. So the debate is about whether it's quantized and what is its temperature dependence.
Sorry, can I ask a question?
Yeah.
On the previous slide, there's some like sharp peaks near the zero field on the left hand side.
Yeah. Oh, that's noise.
That's noise. It looks so. But if you average more times, it goes away.
Yeah. You can tell it's noise because it's just one individual point. Okay, so let me step back a little bit and quickly review the notions of Berry curvature and so on. So I'm sure many of you are familiar with these terms, but it's good to get everyone on the same page because all this will come together and help us understand our experiment. So the reason for Berry curvature is because we think of a lattice, right? And we focus only when the electron has the Wannier coordinate. When it's sitting on the lattice site, which we call R, right? That's the Wannier coordinate. Then that's good. We can put it into our Hamiltonian and talk about it and do all kinds of calculations, right? But you notice that you ignore everything that happens in between, right? So if the wave packet is centered at an interstitial site, we ignore it. Oh, we don't know how to handle it. We don't even acknowledge that it's ever there. And so this missing information was what Lettinger pointed out. So this was known a long time ago. This is at the birth of transport theory of the lattice in the late 50s and early 60s. So Lettinger pointed this out, and then he recruited Walter Cohn, and the two of them founded modern transport theory, linear response. Then Laura Roth, Blount, most of you won't recognize these names, but then there was a pause of 30 years, 25 years, and nothing much was done. Then Michael Berry introduced Berry phase. Chen Niu took it up and then amazingly reproduced Lettinger's calculation, coming from totally different directions, but actually talking about the same point. All right, so we can write the general position of an electron or a wave packet as the Wannier lattice plus the intracell coordinate. Right? So it's taken to the closest Wannier point, and then the leftover I call the intracell coordinate. So if you want to be serious about this, when we write down the Hamiltonian, the simplest possible Hamiltonian, the argument for the potential must include this intracell coordinate. And when you take the curl in K space of this big X, that's called the Berry curvature. So the Berry curvature, being the curl of big X, actually has the possibility of acting on a wave packet as a magnetic field, but the magnetic field is confined to K space. Now, this seems like a very fussy, detail that may not bother us, but it's actually present in all crystals. But if the crystal has is time reversal invariant and inversion symmetric, it vanishes by symmetry. And that's why Luttinger could make this discovery. He was looking at a ferromagnet, and there, of course, you break time reversal symmetry, and he found that this term popped up, and he could actually calculate the current, and he could explain the Hall effect. Right. So I don't know if many of you know this, but when Irvin Hall discovered the Hall effect in Johns Hopkins, he actually was looking at nickel, not at copper or any normal metal. So he could measure this huge signal because he was looking at the anomalous Hall effect. So the first experiment ever done on the Hall effect was actually the anomalous Hall effect. And he was actually measuring the Berry curvature. So Luttinger realized that and said that, well, the whole theory of solids is incomplete. You have to include this term. But it was way too early. Right? So like all his works that permeated today, it's 30 years before its time. And he was basically, he was so frustrated that he walked away from the problem. But anyway, his calculation exactly duplicates what Chen Yu did 30, 40 years later. So this is sort of a qualitative meaning of the Berry curvature. So that's Luttinger. But the most important thing for us is that, when we study transport in the semi-classical regime, all of us recognize these two equations. This is the first thing you study. You look at in Ashcroft and Mermin, right? So it's easy to remember. But if Luttinger were correct, that's another term. So this is the Berry curvature term. I propose we call it the Luttinger term. And it lends a nice symmetry between the two equations. But unless you kill the Berry curvature, you have to contend with this term. And it gives you a Hall effect. In the case of a ferromagnet, it's a charge Hall effect that's very large. But importantly for us here, if it's a thermal system with no charge, this still exists, and it gives rise to a thermal Hall effect. This is easy to see, and I've indicated here how.
This is not quantized.
No, not quantized. It's all semi-classical. And you can easily derive this from starting from these two equations, which I won't pause. Now, the neutral thermal Hall effect arises as follows. We apply a thermal gradient in the vertical direction, right? And the Berry curvature we assume is perpendicular to the plane, unlike our physical magnetic field. The Berry curvature is pointing out of the screen. And what I hope to show in the next slide is that when you apply a heat current this way, this edge will have a higher edge current than this edge. So naturally, you see then there's a net thermal current going to your right. And that is what's observed as the thermal Hall effect. So we will hit each of these points in the next few slides. Okay, so the geometry is like this, as I said before. The heater is here, so you're pumping heat current in the vertical direction. Berry curvature is going into the screen, and you can measure the Hall sensors. If you make a cut in the vertical direction, right, along the temperature gradient, the warmer edge will have a higher occupation of the space in the edge, as I've tried to show here. And so the current carried by this edge is going to be larger than the current carried by this edge. Now, the reason why the current goes around in a circle is because of the Luttinger term, right? So the Luttinger velocity, as from the previous slide, is F, which is now the gradient of the wall potential. But remember that there is a wall potential right at the boundary, right? So this comes down in a very steep fashion. The gradient of that gives you the F. And this will drive the wave packet around in this direction. But when it hits the warm edge, it's going to be heavily occupied compared to the cooler edge. So when you pull all this together, you get a net heat current that should be familiar from the quantum Hall effect, integer quantum Hall effect. It involves the Berry curvature amplitude. Right? And this works for both fermionic or Bose-Einstein particles. In this case, I'm using the Bose-Einstein distribution. And I'll show in a minute why we can rewrite this within some approximation in terms of the Chern number. Right? To go from here to here, we can basically sum over the Berry curvature to give you the Chern number. So this is the final expression that will help us. Oh, I guess I went over the same territory here. So, following Murakami's calculation, so I've already talked about the Luttinger term, and the unbalance between the bottom edge and the top edge gives you the net heat current, and that constitutes the Hall current. Then this is easily transformed into this expression, and then that leaves you a sum over K of the Berry curvature, which immediately gives you the Chern. So this is how we hope to actually make contact with the Chern number just using a simple transport experiment. Okay, let me skip this because this basically covers what I just said. The only quantity that we need from here is that if you take your line integral of the z component of the Berry curvature, you end up with an integer times 2 part. Right? That is the Chern.
But now it's quantized because here we both get together.
Yeah, in this situation, it's you quantize means it.
Yes, it's an integer, right? Whereas in the original, Luttinger.
Yeah. So this is the interesting thing, right? So when we talk about integer quantum Hall effect, because it's fermionic, quantization shows itself as a beautiful particle. Here it's bosonic. Nonetheless, it's quantized, as you pointed out. So you should get a Chern number of 1, 2, or 3. If you get something like a 1.6, then you know you've done something wrong. So it's another way that quantization appears, but not in such a dramatic fashion as a plateau. Okay, simultaneously with our experiment, Yongbek Kim's group revisited this whole problem of spin excitations. And they found that actually with the Hamiltonian that everyone accepts, ruthenium chloride obeys, including the gamma terms, there is a Berry curvature. And so here's a map of the Berry curvature, and there are hot spots. Remember, I mentioned that in the bulk, the spin excitations are Dirac-like, right? So these are the nodes of the Dirac cones in spin. And they are centered here at the vertices of the hexagon. But the miracle is that when you reverse the magnetic field, the physical magnetic field, which is pointing along this direction, the zigzag, when you reverse it, it changes sign. So this is somewhat surprising, right? The Dirac cones where the Berry curvature is intense, is sitting in K space, and you're applying a magnetic field this way. But if you reverse its direction, the Berry curvature changes.
Okay, but those Dirac cones are
They are, it depends on the magnetic field, yeah. In this situation, we, let's see. Actually, I'm not sure. I'm not sure in YB Kim's calculation whether they get. I think they remain unkept. Yeah, it's a different situation from the
So is this what people call a direct spin liquid? Is that what they call it?
No, that's different. Yeah, this is just good old magnet theorem. This is a high magnetic field, not in the spin liquid interval. Okay. So the first question that we addressed was, are the excitations moving along these edge modes fermionic or bosonic? And I want to convince you that this is a yes or no question that is immediately apparent. So what Peter and the rest of the gang did was to fit the measurements to the Murakami expression given here. And you can see that the fit is pretty good. And this is a fixed magnetic field versus temperature. The error bars get larger and larger down here. Now, if this had been fermionic, you would get a constant, which is what the Kyoto group should have checked, right? The data corresponds to this interval between 4 and 6, where it's supposed to be quantized. But there's no evidence at all that it's quantized at any field, whether you're sitting at 9 Tesla or 8 or even higher. So based on this alone, we gravitated towards the conclusion that these are bosons. Right? Another way of saying this is that if you take the Murakami expression, use the Fermi-Dirac distribution for rho, you immediately get the famous Kane-Fisher. And this is what Kitaev used, except for Majorana, nu is in half integer. So this is exactly the 1/6 that Kitaev found. But it's, I think this is the clearest comparison, right? It's either temperature independent or it's temperature dependent. It's bosonic or fermionic.
Like, can you have multiple excitation and then have some combination of those?
Combination.
I mean, some fermionic excitations that give you constant, and then some on top of it, some bosonic excitations that give you.
But that would be very strange, right? You mean a mixture of fermionic and bosonic?
So what you're implying is that the magnons actually have a non-trivial term, is that it?
Yeah, so these are called topological magnets.
Okay.
So we weren't the first to say it.
Okay.
Theorists had already talked about this.
That's what you mean by bosons, that these are magnons. These are magnons that are kind of.
A high magnetic field.
Okay.
Yeah.
Okay.
Yeah. Remember, we can vary the field.
I understand.
I think the curve we just showed, this bosonic from, this curve. I don't know whether I can interpret this way. At 0 temperature, you get just 0. So that means that there's no active state.
At 0 temperature, the entire signal vanishes very rapidly.
But at the final temperature, you'll see something. But this is from excitation, which is see the barrier curvature in the band, you get a computer. Can view this way? So basically, this.
Sorry, I missed the last statement.
You'll see some kind of kappa x1. This coming from the thermal excitation.
Right.
Which because your band have a barrier curvature, the thermal excitation see the barrier curvature, then you'll see something.
No, it's more than that. There is a big gap. Yeah. Hold that thought. So if you look at this, as a Xiaopeng, I guess this is what you're trying to point out, that there is a big gap. There is a gap. Your thermal energy has to vault over this gap to see the excitation, and that's why it's unlikely to be fermionic. Right? So so what is that gap? But this gap was already apparent in the data without going through this fancy fitting. The Hall signal dies up once you get below 4 Kelvin. You have to work very hard to see it, and that's why it's noisy. But I'll come to that in a second. So in the fitting, I should say a few words about that. Oh, so this is true a whole range of fields, right? We actually do the experiment in the perpendicular way. We hold the temperature and sweep the field. But to make the fit, we have to hold the field and sweep the temperature. That's why Peter had to accumulate these gobs of data. But anyway, at every field value we claim Murakami's expression fits very well. And the point of this fit then is that we can now extract a couple of things, two important quantities. One is that we can compare the Chern number, right? Remember I made the approximation that if the, maybe I didn't say that, there are actually multiple bands of magnons, spin excitations, right? And we think only the two lowest ones contribute that we can see, right? And so this provides a way to measure the energy of the lowest band. That's the gap that we're talking about. So we call that W1 or omega 1, right? So that's this term. And then the next band, which will be weakly excited, has the opposite Chern number, because for magnons, the Chern number alternate if it's finite. So it's 1 here and minus 1 here. C2 is just a mathematical name for this particular function.
What is this cutoff U0?
U0 is basically the gap. Yeah, because, yeah, sorry, I made a change of variable. U is data times energy. So it's a dimensionless measurement of the lowest energy, which means this gap here. Then that's important because this provides a sanity check. But you know, it's theoretical expressions. How do we know that it makes sense, right? So we need reality checks. So the first one is that the Chern number is roughly 1.1, right? When you get above 9 Tesla, the error bars are somewhat large, but anyway, it's not 8 or 100, right? It's amazing that you start off with a thick crystal with 100 layers, right? And then you do the calculation in the 2D limit, you get a Chern number close to what? You're not getting 0.1 or 100. So that's the first sanity check. The second one is this energy scale that I mentioned, the omega 1, 0. And the value we get is 1 millivolt. That's omega 1. That's 1 millivolt here. As the field increases, this gap increases, right? But this is exactly what spectroscopists have been telling us for years and years. ESR means electron spin resonance. And I think included here is also neutron scattering. They have been measuring this sharp mode, Magnon mode at high fields for a long time, and their dispersion versus field is somewhat higher. But anyway, this branch especially matches the transport. So that's our second sanity check. We're getting a Magnon band energy that is almost for certain what the spectroscopists see. And you get a magnitude of Chern number close to 1. I think I left out one slide. Yeah, I left out one slide that shows the other microwave measurements. So we feel that we're kind of boxed in, right? The magnitude of the signal is boxed in by the Chern number. The energy that describes this strong temperature dependence, the gap, is boxed in by the spectroscopists. So there's not much freedom, right? So this convinced us that the expression is indeed correct. But you notice that this is only true at high fields, above 9 Tesla. As you progressively polarize the moments with field, the magnons become better defined. But here, which is the interesting interval between 7 and 10 Tesla, where it's a supposed spin liquid, the Chern number is coming down. And so what does that mean, right? We don't know. So this is an indication that this Magnon description is starting to break down. And what the neutron scattering community sees, they don't see sharp modes. It's just a broad background. So we think there's a lot of interesting multiple spin excitation physics going on here. Okay, I think that's all I want to say. There are some groups claiming this is all due to phonons, but these comparisons show that it's not. There's no contribution of the phonon Hall effect, if indeed it exists. We are very dubious. to this experiment. They have different trends, so they don't contribute. So I think I'm going to stop here. It's got long enough. So to summarize the points, we see kappa XY that's very strongly temperature dependent, and it fits this edge mode description by Murakami very well. It's consistent with topological magnons of 10 Tesla, and as I mentioned, they're kind of boxed in by the Chern number as well as the low temperature, the energy of the magnon node. So it agrees with terahertz experiments. So this we think is the first observation of a bosonic sort of integer quantum Hall effect, except it's not as dramatic as the fermionic case. But we can rule up half quantization and as well as the full unlikelism. So, thank you.
Yeah, due to the time constraint, we might only be able to take like 2 questions.
Yeah, I have a question. Like at the end of the talk, you said that the phononic mechanics rule out. But I remember in your calculation, like you from lambda xy to kappa xy, you still need the kappa xx term. But that term, does that has the contribution from Phaun Ong?
Oh yeah, kappa xx does that.
So that won't change. Like for example, if you
like, so you could have a very, remember in the experiment when we hit this end, there's an enormous phononic current. Right? But if you apply a magnetic field parallel to the current, you wouldn't expect the phonon current to be deflected to one side.
No, I'm not saying that it will deflect it. I'm just saying like because like it's deviated from quantization. Is it possible like your kappa xx is wrong? It's not the only the edge contribution. It's only.
We think it can be ruled out.
I see. Is there any other questions?
So this is not in spin liquid phase at the start?
It depends on the magnetic field, right? Because remember the phase diagram, the spin liquid phase is.
Okay, but how is that spin liquid characterized now? I mean, it's just simply absence of ordering.
Absence of sharp modes seen in the spectroscopy.
Right, but the absence of order doesn't mean it's a quantum spin.
Correct, yeah. So you could say that we are agnostic about this. Yeah. So the Chern number measurement starts at around 9 Tesla, right? So somewhere here up to here. But here it starts to deviate from.
So how can we, how otherwise, the goal of this conductivity experiment were to understand whether it's in the correct phase. So
one has to think of much sharper experiments. But it's not Majorana's thing.
Maybe it's equal spin liquid, but now it's a chiral spin liquid. Chiral spin liquid have this quantum Hall, somehow Hall mechanism.
Yeah, but the chiral spin liquid is incompressible. This I think is different.
Yeah, truly compressible. Yeah.
And this would have the chiral spin liquid would have no equals half. Okay, this has no equals 1. So it's not like the quantum Hall effect. For bosons, no equals 1 would have to be non-abelian state. It's not this. I think this is just simply that these magnons have non-trivial from a Chern number. It's a different story.
Yeah, I don't know what you mean. But one of chiral spin liquid is a spin line in a D wave, P plus ID. I think for the Kitaev model, it's a P plus IP, so that you get 1/2. But however, you don't even see P plus IP, so probably maybe time reversal is broken, but there is no chiral edge states. But however, the thermal excitation may see some chirality, but not in the ground state. The chiral edge state is a ground state probably, but that seems not seen by physics.
And I would say, in fairness, not all experimental groups agree with us. So right now there are 4 groups around the world attempting to make a measurement, and 3 of them claim to see half quantization. We are the sole holdouts, but you should look up their publications. It's all published. Yeah, and sometimes they claim robust. The one that's most amusing is one group that claims robust quantization, and the data is noisier than what we would show here. And the title of the paper is robust quantization. So I feel that once experimentalists grab hold of the shiny objects, it's hard to let go.
The problem with experimentalists believe too much.
Yeah, it could be that. Well, you need to get funding, right? Get a paper into Nature.
All right, so let's thank the speaker again. And there's one last announcement. We have to reschedule tomorrow afternoon's Professor Tsenke's session due to a flight cancellation. And I think there's already an email sent to all the in-person attendees. So please check your email, and then we'll make the final announcement tomorrow morning. Thank you.
I still I'm very sure so this is your merit, what your merit is determined, and this is what expected to be quantized, right? In the theory. So that's only counted the contribution from the